Hi, this is Pete Ekman with RoboZone Podcast. This is our Kettering GoPro Corner weekly update that we do every week, and we have a very special one for you guys today. For those that are watching us on Twitch, you'll already see the presentation that Andrew Watchorn, who is our specialist, is online today with us. But first, we're going to check in with John. John, how you doing?
Doing great.
Good. We're almost ready for Kim to be back next week, right?
If she comes back, I mean, once you get there, sometimes it's hard to leave, you know.
Especially when we're still in the 50s.
Ocean is just one of those things where it just pulls you in, you know.
But we have a special guest with us today. Why don't you introduce?
There's a joke on that somewhere, John.
Yeah, that's true. John's bad at jokes sometimes. He's got good dad jokes, though. We've already recorded that. But we have a special guest with us, right? John, you want to introduce Andy?
So many of you might know Andy. He worked for NI for 20 years and would come in and teach you Labview and how to use it and programming it. And that's when, I mean, Labview back then was the preferred, you know, language to program with for you robots and stuff. And he'd come to the events and everything and help teams and stuff. But we're lucky enough here at Kettering to have Andy now at Kettering doing lecturing and doing some teaching and also doing some learning.
Sure.
And there's a lot of things that we want to go over on some of these. But one of them is AI. So to talk about artificial intelligence. And Andy is going to set the stage to both how we got there or are getting there from today's world and how you look and program today and where it's going and the differences of what AI brings to the table and how you get there. So, and if you're wondering about the mask, both of us are vaccinated. And so
pretty soon mine will be coming off. So, because you can't do a smile detector behind a mask.
So take it away, Andy.
Thanks, John.
AI can't do that, Andrew, yet?
What's that?
And AI can't do that for us yet?
And not through the mask. Well, not with the sensors that I have on this laptop. So, and we're going to talk about that. So this talk came from the fact that I took an AI class from Dr. Jung-Mae Park in summer term last year in 2020 at Kettering. And I really didn't understand AI, neural networks in particular, and I certainly didn't understand the difference between them and AI and machine learning and deep learning and all of the things that were buzzwords around what computers can do. And through taking that class, one of the first things I did after I finished it was I met you in the hallway, John, and I was like, oh my gosh, I think that first students could understand the math behind this, at least the math that comes out of it, but use it maybe. And so that's when we did something crazy and we thought about putting this talk together. Now, I want to just curb everybody's enthusiasm at the beginning, which is neural networks and what they do are transformative. They are a thing that we're going to talk about for the next 2 weeks that just is a totally different way of looking at engineering and how computers make decisions and all sorts of things like that. And new meaning that they really only figured this out in the last 12 years. And for some of you, 12 years may be a long time, but for some of us, it was yesterday and nobody knows what we may do with this next. So this is new enough that if you get exposed to it now, and you decide that's something I want to learn at college, you can come in and take classes at a place like Kettering and start to build intuition about what neural networks can do versus what traditional engineering can do that may serve you really well. And you may be one of the first people in your area to get that sort of insight. And then, so I want to curb everybody's enthusiasm. This is not me saying you should use this on your robot. Also, I want to be really clear. You're going to hear me say a couple things about what AI, over the next 2 sessions, what AI can do versus learning the math. I do not want you to hear that you should not have to learn the math. You have to learn the math to keep the AI from going in a direction, I'm sorry, the neural network from learning in a direction that isn't reasonable because you programmed it wrong, right? Or because it got the wrong information from the data it was presented. You have to learn the math. The math is your bedrock. But this neural network approach to artificial intelligence and machine learning is something that may really change engineering. And it's something I consult with a company in Canada named Quanser that does control engineering. And so some of this is based on what I know from them, and some of it is based on what I know from this class. But I really want to thank Youngmei Park, Dr. Park, for that class last term. So I want to start with the idea that there are lots of overlapping terms in artificial intelligence and machine learning and deep learning and neural networks. And I'll share a little story, which is when I was looking for an image that was good, that was simple enough, but informative enough, there are a whole bunch of images that I found where deep learning is inside neural networks. And sometimes neural networks are inside deep learning. And sometimes machine learning is bigger and smarter. So nobody agrees on exactly what to call all of this stuff. But it's important to know that nobody agrees about that, because that means that we're still in an early stage of this. So the way that I've come to terms with this image or model of the world is that artificial intelligence is just making something seem smart. Artificially intelligent, smart systems like a smart thermostat or a robot that can follow a line, it may not have any sort of human qualities other than just it's a little smarter than a robot that doesn't have any sensors on it, right? So that's this big world of artificial intelligence. And I really like the Turing test. Some of you can look this up, but an early person in computer science in the 40s was named, I think it's Alan Turing, Alan, right? I was going to say Albert, but it's Alan. And he says, basically, what if I present you with a machine that seems smart and you can't tell that it's not a human being, does it matter whether it's a human being or not? It's artificially intelligent in a way that you can't tell the difference. So great. So you can make things smart without having them learn on their own and without having them learn in a deep way and without using a neural network. So that's that outside circle. And then machine learning is when a machine can take information from its sensors and start to, based on its history, understand what happened and make better decisions in the future because of what it's experienced, right? But that doesn't mean that it's working like my brain, okay? And then deep learning is where you can do a deep dive into a lot of different paths through what information is coming into the robot. And you have just this very large group of endpoints that could make the machine learn, right? But that may not be doing what the cortex is doing in the human brain. Neural networks are when you are approximating through a mathematical model what happens with with the actual neural networks that are happening in the layers of cortex. And if you want a good book to read on the topic on intelligence, I believe it's a guy named Hawking, out of Stanford's Brain Research Center. That is a great book about how actual neural networks work in your brain. But a neural network in artificial intelligence is a computer using math to simulate that system of how we learn as human beings. So hopefully that gives you some amount of ability to look at one word and another word and say, well, they're not exactly the same thing. Okay, so let's take a big step back. That's where we're going. And we're going to see that slide two more times. You will be visited by the ghost of Christmas past several times in this presentation. So before, I want to now set sort of a ground plane, because lots of you are not roboticists. You're not trained roboticists. And I just want to make sure that everybody's on the same page. So how do computers understand the world around them? Well, they need sensors or transducers. And I just put up one because it happens to be in my laptop. My laptop's got a processor in it that's a brain, but it's also got a microphone that I'm talking through right now. In fact, we never tried this while I'm actually recording. So hopefully I'll be able to use the microphone for me and for this, but we'll see how that goes, John, right? Yeah, we're in for a ride. Yeah. There we go. But you know, the idea is that my vocal apparatus, by the way, my other degree is in music teaching in choir. So I'm really familiar with vocal apparatus here, compresses air. And you can see over here, I think you can see my mouse, but over in one, that compressed air is going to hit a membrane, which is going to shake some electromechanical parts in a microphone. And out of number 5 is going to come a voltage. And then that voltage can be brought into the computer, and then you'll see some sort of pressure difference that happens, some sort of wave that comes into the computer. And we consider that one-dimensional data. And I'm going to bring this up later because neural networks are really interesting because they almost don't care how many dimensions of data you've got. But in this case, we've got one. It's a voltage. This pressure wave has a certain voltage or a certain amount of pressure at any given time. Right? And I know that many of you will say time is also a variable. And I will say that is for an advanced physics class. So we're just going to consider time not a variable. It's one dimension. We don't care. Time isn't going to flex. We're not going at the speed of light. So just relax about that. All right. So this is a voltage at a certain time. That's one dimension, one thing that's changing. You can also have two-dimensional data come into a computer that it can try to understand the world with. I happen to have a webcam built into the top of my laptop, and it's got 2 dimensions of data. What does 2 dimensions mean? Well, time is still happening, but now I'm using some lensing. And I really don't like this picture because it makes it look like you're focusing the light onto the focal plane array. Really, and I put a note down here if you come back here later, and I know for all of you engineers in the background, you're like, that's not how this works. But it was the best picture I could find, and I like it enough. But basically, you'd have a focal point over here, and it would spread whatever image came into the lens onto this 2-dimensional focal plane array. So you've got rows, and you've got columns. You've got 2 dimensions, rows and columns. Right? And now you'll get a value. If it's black and white, you'll get a value of the intensity. If it's black, it might be 0. If it's white, it might be 255, right? And it's also true that you can have multi-dimensional data. So I put 2+ at the top of this slide because you can also have red, green, and blue focal planes that all work together to make a color picture that sort of fools your eyes into thinking it's got full color spectrum. So you might have a 3x3 array here, and a 1, 2, 3, 4, 5, 6x6 array here, and another 3x3 array here that each come together to make a cube of information. And that would have 3 dimensions: row, column, and red, green, blue. A little cube, sort of a flat cube, but fine. So, why do I bring this up? It's because we have been making smart systems for years, decades. So what's new? What's all the fuss about? Well, I want to show you where traditional engineering starts with a model-based design approach, which is what most colleges are teaching right now for a good reason, because it's extremely valuable and extremely durable and gives you insight. Right? And then I want to compare that next week with what happens with neural networks. And I'll give you a little taste of that at the end. But let's just go through the process. If we are going to use a traditional approach to engineering, I might have a system. Over here, I've got a system. This is actually a system from Quanser Incorporated. There happens to be one at Kettering. I ran it last year for an automotive control class. And this simulates 1/4 of a car's suspension system. Now, you have to use your imagination a little bit, but there's a motor down here that drives a screw that can move this plate up and down. That's the road. The road can go up and down. And then you've got a spring here, right? Well, let me see if I can get my cursor. You get a spring here, and that spring is like your tire. Your tire can flex. And then you've got a red plate here in the middle that's like your wheel. By the way, never call your wheel your tire or your tire your wheel, because they're different things. The tire is the rubber part, the wheel is the metal part, and it's got mass. So this is now like your wheel. And then over here, you got another spring just above that red plate before the blue plate. This is your springs, right? That's your spring suspension. And then over here, you've got a plate at the top, and that's the vehicle. So what I can do is use the motor down here to drive what the road is doing. And then I would see how each of these different plates move based on that movement. And what you do as a traditional engineer is you use a bunch of math understanding that you get as a sophomore in college called differential equations to figure out how each of the plates will move based on the velocities and the accelerations and differentiation and integration and all sorts of stuff. And you get this equation down here. And what we find out is that equation doesn't mean very much to you. So what do you have to do next? Right. Doesn't mean very much to me. John's laughing, but it's true. All of us have been through it, right? At the beginning, you're like, what are all those pieces? And so eventually what you do is you learn how to analyze all the parts of a differential equation, and you can figure out, you can get some insight about the system. So once you see all the parts and where the masses are and the springs and the dampers and all of that stuff, you can get some idea about whether or not this is a stable system or an unstable system, whether it can be brought into control or whether it can't be brought into control. So you get insight from the math. So the math, while it's hard and weird, gives you incredible insight into what the system will do later on, okay? Given if you want it to respond in a certain way. And then based on that, you figure out what you want out of the system and you try to understand how to get the system to give you a response that you want. Now, I'm gonna start with my vocal apparatus, right? If I say the word yes, or I say the word no, I might want my computer to understand that so it can respond to me appropriately. If I say yes, it might respond in a certain way. If I say no, it might respond in another way. Well, it turns out that people have looked at this, and yes and no are just different enough, and you'll see that in a second, that you can say a yes has voltages in it that look like this, and a no, oh, sorry, that's a no, and a yes has voltages in it that look like this. They're totally different. So I can just, if I can do that analysis, I can figure out if I say yes or no. So that's sort of interesting, and I'll show this in just a second. And then the other thing you might do is you might try to, with your mathematical understanding of the system, try to bring it under control by closing the loop. And what closing the loop means is that you've got a system here that you've figured out the math of, you see what its outputs are, you bring those back around, and you then make some decisions. You bring that back around maybe here as well, and you can figure out how to close the loop so that if it didn't do what you wanted it to do, it will do what you want it to do. That's called model-based design. I make a mathematical model of the system. I use my engineering smarts to figure out how to make one decision or another. And that's how we make something smart, okay? Now, I'm gonna switch over to some Labview so you can just see this real time, because I like doing demonstrations, and National Instruments hardware and software make it really easy. By the way, I don't have any National Instruments hardware, but Labview has some functions in it that can allow me to look at my vocal signal. So I showed you something I found online for the vocal signal that would be about yes or no, but I can run a program here that will take 3 seconds of data and look at it. So I'm gonna go yes, 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 no, no, no. Okay, so I got 3 yeses and 1 no. I didn't time that very well, but for time's sake, let's just imagine that this is a yes and that's a no. Now, can you see where the words start and stop? Pete, can you see where they start and stop?
Yes, I can.
Yeah, you can. So all you have to do now is say, all right, well, I want to zoom in on a yes. And if I think I know what yes does, all right, so yes looks like this at the beginning. It does that, and then it does that, and then it sort of rings through, right? And then if I come back out and I look at no, I can do some analysis. And what I'm going to do is I'm going to build a model. Look, no is totally different, right? It goes up and down, but goes up and down in a different way. So if I can capture that in math, I can now say, look for that signal or that shape, and maybe that's a yes or a no. Okay, pretty neat, eh? And let's take a look for a second at two-dimensional data. So I'm going to grab, let's do this. I'm going to start the Vision Assistant. And let's just say that I wanted to figure out when my mouth is open. By the way, you can tell when my mouth is open because I'm breathing. Right, John? I'm just kidding, because I clearly talked a decent amount. But fine. That's not that is not funny. You're not supposed to laugh at that.
So that was a pretty good one.
And I'm just going to acquire an image off my USB camera that's here attached to my computer. And let's see what I can get. All right, so let's see if I can, there's my integrated webcam. And let's see if I can get an image to happen. Oh, may not be able to. Oh, camera can't do it. So we'll have to do an audible because you can't run the camera while you're also looking at me through the webcam, but that's fine. You can imagine that I would have taken a picture of myself. I would have opened, if I was looking for my open mouth, I would have said, all right, there's a dark spot in the middle. And there's some other spots here. I would have maybe extracted a color plane so it would be black and white. And I could figure out the edge strength in the same way that I've got a voltage change strength here. In a picture, I will have, if I go from something dark to something light, I might have an edge strength that's very strong. And in about a couple minutes, I could basically make something that if I was sitting in the same spot all the time, I could look at a spot on my image of my face and it would say, you've got an edge strength down there. You got an edge strength up here. That means the mouth is open, which means your mouth is open. And I could measure the distance between those points. But it's because I know something about where the face is going to be. I know what my face looks like. I know what the math is behind how the photons go through the lens, right? So in both of these cases, the engineer is smart. The engineer is using their understanding of the world to make a decision, and then they're going to program that into the computer. Now, one thing I can show you. Yeah, go ahead, John.
So sometimes when you're driving in your car and stuff, especially new cars, right? It will, on the display, tell you to look at the road.
Yeah.
Wow, how's that happen?
Well, how does that happen? So what it's doing is it's got a camera looking back at you, either from the steering wheel or from the dashboard somewhere, or it could be up in the rear view mirror. And it's looking and it will say, all right, I see eyeballs because I know what eyeballs look like, right? I can see where those edges are and I can see where the black spots are in the middle. And they do not seem to be, and I know what the geometry of that car is because I know where the camera is. I know where the driver probably is. And the thing is going to say, those eyeballs are not looking at the road. So if I'm doing this, it can't see my eyeballs anymore, right? And it goes, oh, I've lost eyeballs, which means either you had a stroke, John, which you don't want to have while you're driving, right?
That's a bad thing.
You certainly want,
anytime.
if you do, you want the car to know and call an ambulance, right? Exactly, right? So, or I've fallen asleep, or I'm looking down for the keys that I just dropped, or the coin that I just dropped, and the car will say that's not safe, but that's image processing. By the way, so one thing I can show you is you can mitigate. So one of the things I said is the engineer's smart, it can figure out whether my mouth is open, but I got to be in the right spot. So I've got to have the region of interest in the right spot, looking at a face that might have a mouth that's open in it, right? So the engineer has to have put a lot of thought into making sure that everything's in the right spot. Well, as we get better at image processing, you can do things like this. So this, by the way, this is a battery bracket, and you might think of this on an assembly line. So somebody's stamping these things out and they want to make sure if they're okay. And the way that you know if they're okay is if the distance between the top thing and the bottom thing, I don't know what those are called, terminals, flanges.
Yes, battery clamp.
There you go. We'll call them terminals for now. I like that, Pete. So if the distance between these is right. So what I've done here, or what I'm showing you, is a program that when it's run, it finds, first of all, where these holes are. Notice, I'm going to stop that for a second because it's like chasing a fly. It finds out where one of these holes is. It looks on either side for another one of the holes. It says, okay, I found two holes that are the right size. And so that means that this is the end of the bracket, which means I'm going to be measuring something over here, right? And so that's what this does. And it doesn't matter what orientation that is now. But still, this is not a system that is learning how the parts are made. An engineer said, I know that there will be two holes. I know that there will be a place that I'm measuring, and I know they will be this far away based on the geometry of how far the camera is above the assembly line. But you can get some pretty smart things to happen. Artificial intelligence, right? And this is figuring out where everything is set up, but it's still the engineer that's smart, okay? So again, if we come back to this idea here now, the engineer being smart can say, oh, I know these voltages mean no, These voltages mean yes, so I'm going to put that in place. I know the dynamics, which is that differential equation about the system that was the quarter car. So I can now bring that under control. By the way, bringing that under control, John, that's how your stability control in your car works. So it can basically stiffen and loosen the suspension when you go over a bump, because it goes, oh, that shouldn't have happened. And it figures out what to do. That's called active suspension, right? Yeah, okay. That's what that shows you how to do, which we teach in the automotive control class here at Kettering University. So I can bring that system under control using the math that I know. But what happens, John, when I go, yes, great, no problem for my computer. But what if I go, yep, is that the same? Well, it's got the same beginning. What if I go, okay? What if I go, uh-huh? Well, now I got to take into account. You're messing with my math. I'm messing with your math. And I've got to now, as an engineer, go, oh, okay, well, if it starts uh-huh, then we got to figure out if it becomes uh-huh. And if it starts yes, it could be yes or yeah, but it could be yellow, which isn't the right answer, right? And so all of a sudden you start to get a lot of complexity. Now, just to show you that this is a smart system, but where complexity is added by the fact that there are lots of different ways that something could go, right? This could be a robot that's learning to play soccer or football, right? Depending on which part of the world you're from, right? Well, what does this say? All right, we start our robot going, and the coach is telling us to score, right? And then, well, do we have the ball? Do they have the ball? Do we not know where the ball is? And you can go down through a decision tree, which will help a robot seem smart. And it may even, if you remember what you've done, learn a good decision to make in the act of doing a soccer match, or of participating in a soccer match or a football match, right? But this is what I would consider still a traditional approach to artificial intelligence, even a traditional approach to machine learning, right?
So let me ask you a question, okay? If this was for a chess game,
yeah,
right? Is it my move?
Yeah.
Is it not my move, right? And then you go through, and then it figures, oh, I moved my knight to king's bishop 4 or something like that.
That's right.
Right? And when I do that, this happens. When I do that, it could.
So the nice thing about chess, and why you can do machine learning, is it learns based on the way the chess pieces are set up. But it's what we call a bounded set. There's only so many places those pieces can go. And in fact, and you can talk to the IBM people if you ever get in touch with them, right? Right. But what I think I understand about the world is that Deep Blue just took a decision tree like this, and it had so much computing power that it could store all the possible options, and it would just make the right move no matter what you did. No matter what you did, it would figure out, but it took a lot of processing power. And that's not what we're talking about necessarily either, I don't think, but you can verify that with the IBM people. So let's come back to, now let's land the plane for our first session here, which is what I've just talked to you about is model-based design. Model-based design is you as the engineer are smart, and you can add smarts to a system because you are smart and you know the math. And the math tells you that the system should work a certain way, okay? And you can also apply that to machine learning by saying you can give different paths through a problem. You can even remember what you did before, but it's still the engineer that is programming all of those paths and deciding what is important and what happens. Even deep learning. And that's why there's this weird thing about whether neural networks are in deep learning or deep learning is in neural networks. And sometimes I've seen that one just removed anyway. But even deep learning is just how deep those paths go to make that learning, relevant to your situation. Neural networks are different. And this is my opinion. And again, other people may disagree with this, but having learned about it and having worked in the industry for 20 years, this is a fundamentally different thing. And so this will whet your appetite for next week. That's a neural network. So the way that your brain works is you have inputs and sensors, and they go into this thing called cortex. And cortex, and we'll talk a little bit about this at the beginning, so I'm not going to go deep into it, but it's like 6 layers and 1 trillion neurons, no matter what it is. And this is interesting, John. This is from that On Intelligence book. Your audio cortex is the same as your visual cortex. It's the same structure. Your memory cortex, same structure, same structure. All of the outer cortex, not the middle parts of your brain, not the parts that are about your emotions and how you're feeling about stuff and when you're hungry and your autonomic system. That's all not the same. But cortex, all the stuff around the outside, it's the same in every direction, which is why it was so hard to figure out. And it's built up of layers of neurons. That's the key. So your sensors go to the top layer of the neurons. And you can think of the sensors like an input layer of a neural network. If I take an image, 2-dimensional image, and I flatten it out into all of the pixel values, right? I just flatten it into a 1-dimensional array. I can put those into a system, right? And I can have this pixel tell each of these neurons whether they should activate. This is what's coming. And then whether they activate or not, or how strongly, can tell each of these neurons how to activate, whether or not to activate. And each of those neurons can make each of these neurons decide whether to activate or not. And then at the output layer, after you've gone through those inner layers of neurons, and this all happens in math, and this is what I'm going to show next week. It's so neat because the math is so simple, but this is the idea. The way these things activate or don't activate will tell you whether John is in the picture, or whether the mouth is open, or whether you see a goal, or whether that's a 9 or a 1. So next week, I'm going to show this applied to handwritten letters. You make a 9 in a different way from me. You say, yep, I say yes. You say, uh-huh, I say, okay. All of that stuff can be translated into, that was an affirmative answer. So it goes through a neural network, and this thing says, that was an affirmative answer. And it doesn't matter what the math was. And the best thing, John, and this is the neatest thing. So the second part of next week is going to be the fact that when I train my neural network on thousands of pieces of data, and we'll talk about this in a second, but when I train it, it will then back propagate and minimize the neurons that made my answer wrong. If I get the answer wrong, if it was a yes and it was actually a no that you said, it will backtrack that through all of these neurons and make them either more important or less important. And then you'll run it again. And if you still get the wrong answer, it'll go back through. And that's called training a neural network. You go back and forth through the math, and all of a sudden, in between the neurons, you get a model for the system. And you didn't have to know anything other than the basic math of how to change things, which I'll talk about next week. So let's talk about why. So that's neat. That's super cool. Now let's burst the bubble a little bit. Okay. Where is this useful? It's only useful, and I'm talking about classification. There are lots of uses for neural networks. I'm only talking about classifying something. That's like saying there was a cat in that picture, there was not a cat. That was someone saying yes, that was not someone saying yes. John is in the picture stroking his beard. John is not in the picture stroking his beard. That sort of classification. Is it one thing? Is it another? It might be really useful for a first robot, but you got to have 4 things at least. I'm not an expert. So this is just Andy Watchorn's starting off point. You got to have lots of data. If you have thousands of pictures that have John in them stroking his beard and John not in them stroking his beard, if you have thousands and thousands and thousands of pictures, that's what you need to train that network. You're going to train the network on every picture, and it's going to have to learn when it's right and when it's wrong through the math that I'll show you next week. Number 2, it's got to be labeled. This is the hardest part. It's not just that you got to have the picture, but you've got to have it appropriately labeled. John is in this picture. Or if it were my vocal signal, because I don't want you to think it's all about pictures. It doesn't have to be. You've got to have them labeled. That was a yes. That was an affirmative. That was a no. That was a negative. All of them have to be labeled, usually by somebody. And that takes a lot of time. So you need a lot of time, a lot of data, and you need somebody to label all that data. Once you've done that, you also have to have, and we'll talk briefly about this, and this is where the math gets a little complicated, but you don't have to know it because the math that comes out of it is easy. You have to have a cost function. What is a cost function? It tells you how wrong you were. What was the cost of being wrong? And what part of the system created that cost of being wrong? And that's how you correct the neurons later on. So you got to have a good cost function, and we'll talk about one that's used next week. And then you have to have a lot of computing power because all of those neurons, I don't know if you noticed, but in that picture, all those interconnections are computation points where when I set the system up as a smart engineer, I say, take the data, look in this one spot, figure out if there's an edge there or whatever, right? Look at this data, figure out if the vocal signal does this. And it doesn't, it's just one path through the system. Here, there are hundreds, thousands of paths through the system that we have to calculate, which is why this didn't happen until recently, right? A, the math of that bout calculation didn't exist until I think 2012 or 2011 in any form that was usable. And B, there wasn't enough computing power until then to back calculate enough to train a network in an amount of time that made any sense so that you could get good outcomes from it. And so I will leave us with that as the idea of what we're going to talk about next week. We're going to go through forward propagation, where we take data and we send it through a neural network. And we're going to discuss what the math is that propagates forward to an answer. And then we're going to talk about back propagation, which is where you figure out what your answer was that you figured out, what it should have been, and how to change each of the parts of the system to get a better answer next time, which is part of the act of training the neural network.
So when you take a class, you should buddy up with somebody who's really good at math?
No, because the computer can do all this, John. The math is actually dead simple. That's why I wanted to have this talk with everybody, because when you actually get to the math that propagates through the system, even though you had to know how you got it, right? You just have to know that, right? Or you have to believe that it came from the right spot. But the math is literally addition, subtraction, multiplication, division, and squaring.
Oh, good. I got a
That's
calculator for that.
No, you got a computer for that, right? And the great thing is, if you're using Python, if you're using C, you have to multiply matrices together. We'll talk about that next time. If you don't know what that means, look it up. There's lots of great examples online to talk about matrix addition and subtraction and multiplication. That's how you do all those lines between the neurons. That's a matrix, right? But then the other parts are literally algebra done, not even algebra, just arithmetic done backwards in as many paths as there are through the neural network. And the computer will do that for you.
I have trouble doing it forward.
Well, we'll have to talk about that, John. Yeah. We'll have to talk about that. But that's where we're going. And I like it because I don't know if this is useful for FIRST. I really don't. But what I know is that it's at least approachable. And think about it. Does anybody have a bunch of pictures of the next year's course?
No,
because they ain't made it. I'm sorry, they haven't made it yet. Sorry, John. Every once in a while, I want to get excited. So that's a good one, by the way, for vocal recognition. What do you do with ain't, right? Is that a yes? Is that a no? Anyway, fine.
Ain't knowing.
Yeah, but the interesting thing is nobody has pictures of that field, but we got a whole bunch of robots and teams, thousands of teams around the world that could take a tremendous amount of data. And they've all got freshmen. I'm just kidding, freshmen. You're a valuable part of the team. They got freshmen that they could look at that data and say, yep, there's a goal in that. There's not a goal in that. They could label the data. And maybe there could be a neural network inside of one of these robots that helps it decide when a goal's in the picture, where it is, and what happens. I have no idea whether that's possible, but it's not impossible, is my belief.
But but behind that, let's take a step back and say, wow, it might be easier to use a camera and recognition and traditional programming to be able to program your bot to find the target.
For sure.
Right. But by taking the time to look at or dive down, let's say, into a little bit of what AI can provide and learning the math and learning what's behind it, it's really going to help the kids on the team have a better understanding of what's coming, how things are processed. And also, if they do take the time to do that, when they apply to college, is they're going to go, wow, you played with AI already?
Right. Even if it was a couple layers, and that's what I'm going to show next week. I'm not going to show a 20-layer neural network because you don't have to. But to get the concepts down, I'm going to show a 2-layer neural network with 50 neurons in one layer and 25 neurons in the next layer. And it'll learn how to figure out what digits are written, handwritten numbers, 0 to 10, 0 to 9, pardon me. Mm-hmm. So that's where we're going. Any other questions? Any questions from you, Pete? What do you think?
My mind's blown at this point. I'm going to think about everything. I'm going to
rewatch it again on half speed.
No, I got it. I want to make the joke because I didn't get to make it earlier. Because I want to interrupt your presentation that if people don't know math, then they're not preventing Skynet from taking over. Because if you know the math, you can prevent Skynet.
You can hack the neural network, and that's probably true too.
Here comes Arnold.
Number 2, we're going to do a
learning machine.
A lot more promotion of this for next week. Because I think there's going to be a lot more questions after this, and we're going to release this out on our YouTube channel because the presentation and an audio podcast doesn't really, describe it. So we'll point people to the presentation. We'll put the video on our YouTube channel so people can actually see your presentation. For next
great. And hopefully I talked through enough of it that they'll get a visual.
Oh, I think they do. I think
if they're listening to it.
Yeah, I was thinking about that in the back of my brain. If you're listening to the audio podcast, you can go to the YouTube channel if you just want to know more about exactly what he was talking about and then see the presentation.
Great. Well, thanks guys for the opportunity. And would you just remind people not to ask hard questions?
Oh, you don't know the audience. I can't even get that to stop on my robotics team. How am I going to stop that from you? So, Andrew, I want to thank you for coming on board for the part 1. We're going to have part 2 next week. Seeing Bat Station, seeing Bat Time, 4 p.m. Eastern Standard Time on this Twitch channel. This is RoboZone. TV or RoboZone podcast. RoboZone pod. I can't remember what it is exactly. But before we go, I have to ask John what the update to Kettering Kickoff is, because I got an email from First saying that off-season events have a green light. So that means you have good information for me.
It is. We're moving forward with it as of today, but who knows what tomorrow can bring. We are planning it, moving forward with it. We're going to have September, 18th, 19th?
18th and 19th.
And we're going to have 2 separate events, one on Saturday, one on Sunday. So we can get as many teams through and they can practice and feel good and stuff. We may say things like you can bring some of your people seniors if they're around because they never got a chance to drive and things like that.
Makes sense.
We're talking about doing.
Mm-hmm.
So, it's on. We just have to figure out as closer to we get to it that how many people can be in there, and things like that. I don't know how much stands we'll have because if we do the regular game from last year and this year's skills challenge, which is really half a field, that takes up, a lot of room in there.
Yep.
Takes away tables, so you can't sit down, as much and eat and stuff like that. Because we don't know. We'll probably have some food trucks come in and things like that. But it is on, it is going, and we are moving forward with it.
That's all I want to hear. Positive information.
The other thing is, as we go through these 2 AI sessions with Andy, Friday, I have a call with the chief scientist from IBM's research division to talk about AI. Actually, it's also going to be on COVID, a little bit about how they help.
Oh, they're using AI
that,
to
and
neural
what
networks
if you
to
went backwards?
genetic
And
algorithms.
how long it would take it to, figure out, how long it was for the next one, things like that. But also, I want to talk to them about what else, IBM has for the past 20 or 30 years had more patents than anybody else in the world. So that means there's a lot of smart people there, but how do you get what they're doing out and talk about some of the things they see, going cryptocurrency? What do they see there? What's going on there? What created that? Blockchain? What's blockchain? Have people talk about it.
Oh, John. Don't get me started on blockchains, because
I'm an investor. I want to know about the blockchain.
Cybersecurity, what's going on there? Things like that,
sure.
especially with AI, right?
Sure.
So I'm going to talk to him, and hopefully I can get a bunch of people. I know he's out there already committed to do AI kind of things. So that goes from Watson Health to sure. From a triage kind of a thing being in there, and all sorts of other stuff in cancer research and things. But there's so many other ways you can play with and what they see and what they're doing. But I want to go deep, and I want to go wide.
Okay, not a problem, Andrew. What I'm going to do for next week, I'm just going to call you Andy.
That's fine.
Andy. For next week, what I'll do is I'll put in our audio podcast, I'm going to put the link to the YouTube video, because we're going to put out like I said I would. And then I'll gather any questions from everyone and try to get those to you before we have the recording, so you kind of have a bit of an idea, because we can't, we could talk for hours, right? But to be respectful of your time and what we're doing, I'll see if I can get those together, get them to you.
There's a lot of math to do next time, so just we only may be able to get to a couple questions. Okay, carry on.
We don't want to create brain rot or set John's hair on fire, because there was a couple of times where I saw some smoke start. So.
You should have seen the first time I explained it to him.
Brain cells,
you really should.
You mean this isn't the first time?
No. I showed it to him at some point, and he almost did.
This is about the fourth or fifth time, and
now he's finally getting it.
Okay?
There's a Chevy joke there. I'm just not going to pull the trigger on that one. Yeah, you guys can mull that one over afterwards.
Yeah.
But I want to thank you, Andy, for stopping by with us. We look forward to having you again next week. And John, if I don't hear from you, we look forward to having you back on next week. Maybe Kim, maybe no Kim. We don't know yet, but we'll get there.
We don't know yet.
Okay. Well, you guys have a great week. We'll talk to you next week. Thank you for stopping by.
Hey, you too, Pete.